My name is Junaid Shanifar from Huawei Island Research Center, and I'm presenting our work titled Less Traffic, Better Outcomes, Computation-Aware Request Dispatch in Real-Time at Exchange, accepted at AdKDD 2026. This work was carried out jointly with colleagues from Huawei Island Research Center and Huawei in China. In this presentation, I will explain how selectively deciding which bit request to send to each DSP can reduce unnecessary traffic while improving marketplace efficiency and monetized outcomes. Let me start with basic RTP flow. A user opens an app or web page. The publisher sends an ad request to the ad exchange. The ad exchange then sends bid requests to several eligible DSPs. Each DSP decides whether to respond and how much to bid. The exchange runs an auction, selects the winner, and returns the winning ad to be shown to the user. Our work focuses on the step before the auction. We decide which DSP should receive the request. This is important because every forwarded request consumes DSP compute, latency budget, and potentially bidding capacity. Problem is over-distribution. In many RTB systems, the exchange forwards nearly all eligible requests because more traffic is assumed to create more competition. In our production environment, fewer than 40% of forwarded requests receive bids. This wastes compute and latency, but more importantly, it can trigger DSP throttling and reduce the quality of effective participation. So the optimization target changes. Traditionally, filtering asks only whether a DSP is likely to respond. We instead ask whether sending this request to this DSP is likely to improve the auction. That requires considering both response probability and the possible bid value compared with the competitive context of the current requests. The system has two parts. Online part, it performs lightweight inference and samples dispatch decision in real time. Offline part, it learns from auction logs, retrain the bid models, and update per DSP thresholds. This keeps online serving simple and fast, while still allowing the policy to adapt as market conditions change. The first technical component is distributional bid modeling. For each request DSP pair, the model predicts the probability that the DSP will return a bid. Conditional on a bid, it also predicts a gamma distributional over bid values. This matters because two DSPs may have a similar response probability but very different chances of beating the current competition threshold. In production, we use a bias-left DCN architecture. Request features and DSP-specific features are embedded, passed through a shared DCN encoder, and then sent to two heads, one for field probability and one for gamma bit distribution parameters. Late DSP fusion reduces CPU cost while preserving prediction quality, which is important at production scale. The dispatch decision works in three steps. First, each DSP receives an opportunity value, field probability multiplied by expected bid value. Second, the system forms an opportunity thresholds from the sorted candidate values in the current auction. Third, it converts the probability of betting these thresholds into a forwarding probability with an exploration floor to preserve future learning coverage. Fixed thresholds are not enough because DSP behavior changes over time. Budget availability, passing decisions, throttling, model updates, and changes in the incoming request mix can all alter how the DSP responds and bids. In addition, changes the thresholds for one DSP may affect the competitive environment seen by the others. For this reason, we formulate threshold tuning as a reinforcement learning problem. Rather than manually selecting one fixed configuration, the agent periodically observes recent marketplace feedback and learns which threshold adjustments leads to better longer-term outcomes. We use PPO because it provides stable policy updates while optimizing several coupled continuous parameters at the same time. The PPO state summarizes recent fill rates, requests value, bit distributions, DSP RPM, and action outcomes. Its actions updates two parameters for each DSP: the competition threshold, which controls how strongly a DSP must be expected to compete, and the fill threshold, which filters low response traffic. The reward balance actions value represented by the highest bid with request efficiency represented by DSP revenue per thousand requests. The platform serves more than 20 billion requests per day, and dispatch latency must remain below 7 milliseconds on CPU. For safety, the system keeps minimum forwarding probability on high-value requests, bounds thresholds updates, monitors revenue and latency, and supports automated rollback. For evaluation, we use offline reply and online production experiments. Offline reply compares strategy ordering but cannot fully capture DSP adoption. Online, E1 to E3 tests single DSP in mid RPM traffic, and E4 is the main full inventory multi-DSP deployment with bucket D as treatment and bucket A, B, and C as control. We estimate impact using relative DID. Offline validation shows why the method is not just traffic cutting. Random filtering reduces requests by 35%, but also reduces highest bid by 35%. The best static threshold improves efficiency, but cuts less traffic. PPO reduces requests by about 35%, slightly improves highest bid, and increases DSP RPM by 56.1%. The single DSP experiments provide a staged validation before full deployment. Across E1 to E3, request volume drops significantly from 34 to 71%. Fill rate and DSP RPM improve consistently. Revenue gains are strong in E1 and E2, while E3 is approximately neutral, showing that value depends on DSP and inventory conditions. The main production results comes from E4. In the recent 40 days post-adoption window, DSP requests decreased by 34.2%, while DSP responses decreased by only 6.7%. Fill rate raises by 41.8%, DSP RPM raises by 59%, net clicks increases, and net revenue improves by 4.6% with high statistical significance. Low RPM traffic represents more than 96% of requests, so it dominates volume metrics. But the strongest revenue gains come from mid RPM traffic, where net revenue increased by 10.5% in the recent 7-day window. This shows why aggregate highest bid movement alone is not the right success metric. The per-DSP analysis suggested competitive advantage. DSP receives fewer requests but more responses and higher highest bid at stable bid prices. DSP-B improves bid prices, ECPC, billing relative, and revenue. The policy does not simply raise all prices. It concentrates each DSP and traffic where it is better aligned with the available impressions. To conclude, more traffic is not always better in RTB exchanges. Our computation-aware dispatch framework combines distributional bit modeling, probabilistic forwarding, and PPO-based threshold adaptation. In production, it reduces DSP traffic while improving efficiency and revenue. Thank you for watching this presentation.